This night seems different from others. But what happens here can happen anywhere, anytime. People getting together like millions of others all over the world for a ringside seat of what will happen now. Thanks to television. Television bridges time and continents. The reality of the moment. The world beyond the seas, like we were there. It seems so real because it's naturally in color. A television set is about to be created, combining a large number of electronic components made by the same manufacturer, including the color picture tube. Hundreds of components like these are needed to reveal our colorful world through our color picture tube, one of the most successful in Europe today. A color picture tube can only work properly when its design is good, when its parts are correctly made and assembled. Let's look at how it works. The high-quality glass envelope of the color picture tube is made up of three parts: the neck, the cone, and the screen. The inside of the screen is coated with fluorescent substances which light up when they are hit by electrons. Close to the screen is a perforated mask. The neck of the tube contains an electron gun system which generates 3 beams of electrons. Deflection coils produce magnetic fields to deflect the beams. The electron beams pass through the perforated mask and activate the corresponding fluorescent substances to produce our picture in natural colors. The production of a color picture tube calls for research into new principles, new materials, and the development of new methods of production, massive investment, and human skill and experience. The electron gun systems are assembled in air-conditioned rooms, like this. The air is filtered so that no dust particles can affect the quality. The people who work here need a sharp eye, a steady hand, and the ability to concentrate. Some of the parts of an electron gun assembly are barely larger than a pencil point. The heaters are welded to their supports and closely inspected, and then fixed to the cathode. An electron gun assembly requires over 115 separate parts to make it. Each one a vital part of one of the most successful color picture tubes in Europe. They're assembled by hand on jigs like this. Although this work looks simple, great concentration is required to make sure that all the parts are placed in their correct positions. Insulating glass rods to support the electron gun assembly are preheated. And the gun assembly is firmly anchored to its supports. A cathode is now inserted. This is an important step, as the separation of the cathodes from surrounding electrodes is vital and is carefully checked before welding. Our company developed the first reliable quick vision cathode, which gives us enough electrons to produce a picture in 5 seconds. Now the electron gun assembly is almost complete. The electrodes are welded to the pins of the picture tube to provide the connections to the outside world. Finally, the centering unit, which positions the guns in the neck of the tube, is welded on to make the complete assembly. Let's look how a beam of electrons is produced. When current flows through the heater, the hot cathode builds up a cloud of electrons. If we apply voltages which are positive with respect to the cathode to other electrodes, the electrons will be attracted and then accelerated to form a slim beam. By varying the voltages, the gun behaves as an electron lens and enables us to focus the beam to obtain a sharp picture. By using a negative voltage on one of the electrodes, we can control the brightness of our picture. And we can do this independently for each of the 3 beams. So here we have a completed electron gun assembly, the vital source of the 3 beams of our picture tube. Here it is given a final check. An essential contribution to its success is given by the people who make it. Their experience and skill are every bit as important as the machines that help them to make a vital part of one of the most successful color picture tubes in the world. Here we see the 3 electron beams. As they enter the aperture of the cone, they will be influenced by the magnetic fields of the deflection coils. To produce a sharp picture, the 3 beams must converge to a single point in any part of the screen. How do we obtain this convergence? When there is no deflection field, the 3 beams will converge to a point in the center of the screen, on account of the position of the guns. If we wish to deflect the beams in a horizontal direction to maintain convergence, we must apply a pincushion-shaped magnetic field to counteract the astigmatism of the electro-optical system. To achieve convergence in a vertical direction, we use a barrel-shaped magnetic field because the astigmatism is in the opposite direction. Therefore, the electron beams which pass through the combined magnetic field in the center of the coils will automatically converge to a single point anywhere on the screen. The deflection coils we need for this purpose are quite complicated in shape in order to produce the complex magnetic fields we need for convergence. Only through extensive research has it been possible to design deflection coils that can be made on automatic machines with the necessary precision. These pins, inserted by compressed air, arrange the windings into sections to ensure that a precisely defined magnetic field is obtained. Now the coils and their supports are assembled to form the deflection unit. A high-quality ferrite core ensures maximum field intensity in the cone of the tube and limits stray magnetic fields to a negligible level. The resistance of the windings is automatically checked. Finally, there is a 100% check of convergence. and raster symmetry. Glass, an important, though difficult material. But all our glass components have the same high, uniform quality. For with over 80 years' experience of making and using glass, no other electronics company in the world has as much experience as we have. Every few seconds, a new picture tube screen is molded. Each time glass is heated, it is slowly and evenly cooled down under carefully controlled conditions to avoid sudden contraction. Here, 4 steel pins are fused into the screen to support the perforated mask at a later stage. After controlled cooling, the screen is polished and washed. The neck and the cone are automatically joined together. On machines like this, under carefully controlled conditions. The high tension connector is then inserted into the cone. The mating surfaces are carefully ground to size and then washed to remove all loose particles. After washing, the inside of the cone is covered with a layer of partially conductive material to make sure that the circuitry is reliably protected against any sparking inside the tube. We call this soft flash. As the screen is to be joined to the cone, we apply glass bonding paste to the edge of the cone where it will join onto the screen. Let us see how the electron beams are made to select the appropriate colors on the picture tube screen. The screen has to be coated with fluorescent substances arranged in alternate vertical stripes to produce green, blue, and red when they are activated by electrons. If we place a mask with slotted holes in the way of the beams, we can make one beam activate only the green material, another beam the blue, and another the red. The other two colors remain in the shadow of the mask. That's why we call the mask a shadow mask. We can show how all nature's colors can be obtained with the right amounts of the 3 basic colors. With only the green, we get this. With the blue, with the red, and together. Our shadow mask is made of soft iron, only 1.5 of a millimeter thick. The material is thoroughly washed. And then coated with a thin layer of photosensitive material on both sides. In this automatic exposure unit, the thin sheet of coated iron is sandwiched between two glass plates bearing the negative pattern of the shadow mask. Both sides are exposed to ultraviolet light. Let's look closer at this. The negative pattern of the slots is wider on one side than the other. When the unexposed material under the negative pattern is washed away, we can etch away the iron to give us a hole which is tapered on both sides. This is necessary to avoid reflections from the inside of the holes. Look, if the hole was the same size on both sides, here they are reflected, and here they are not. The shape of the hole avoids reflection. The etching liquid and the remains of the photosensitive material, 320,000 tiny slotted holes have to be etched into a surface the size of the picture screen. The masks are cut off. Careful inspection shows how the slots in the shadow mask are accurately tapered. An essential feature for the successful operation of the color picture tube. After annealing and cold rolling, the masks are given their final shape in a deep drawing press. This is a critical moment because the holes must not be deformed. The mask must be made rigid by means of a mounting frame. It is supported by springs made of bimetal to compensate for expansion due to the heat when the picture tube is in operation later on. Finally, a black layer of iron oxide is formed on the surface of the mask by water vapor and heat. This layer helps to dissipate the heat formed by the electrons hitting the shadow mask during operation. Now we take the glass screens and insert a distance piece, which will provide the correct spacing for the shadow mask. The mask and its mounting frame are buttoned onto the steel pins in the glass screen. The frame and the mask are welded together now. This process is done on the conveyor belt in programmed, automatic spot welding machines. From now on, the shadow mask and the screen stay together through all the remaining stages of production. The exact distance between the shadow mask and the screen is extremely important for good picture quality. The spacing between the mask and the screen is checked automatically. The results are evaluated, the test has been passed, and the shadow mask is finally ready. The next operation is to coat the screen with the fluorescent substances. First, the screen and the shadow mask are separated from each other, and the inside of the screen is cleaned with dilute hydrofluoric acid. The shadow mask, which will be used in the coating process, is cleaned in an ultrasonic bath to remove any loose particles. These are the fluorescent powders we use for making the screen coatings. They only produce their true colors when they're activated by electrons. Here you see them in ultraviolet light. In daylight, or in sodium light in this case, they all look alike. The fluorescent powders are made into a thick, creamy suspension with photosensitive material and applied to the inside of the screen, one at a time. Before a suspension is applied, it is carefully checked for density, viscosity, and electrical resistance. Here, an accurate quantity of the fluorescent suspension for green is delivered into the rotating screen. The coating flows very evenly over the inside surface of the screen. That is why we call it flow coating. And the layer is dried under radiant heat. In the flow coat room, the fluorescent materials, which are products of our own research and manufacture, are applied to the screen in very clean conditions, where the temperature and humidity of the air are accurately controlled. When the layer is dry, we insert the shadow mask, which we use like a photographic negative, while we expose our fluorescent layer to ultraviolet light. The screen and the shadow mask are accurately held in position in relation to the light source by clamps. We simulate the effect of the 3 electron guns by placing our ultraviolet light source exactly where each of the guns will be in relation to the screen, and use a special lens and filter to give the effect of the deflection yoke. For green, we place the light source where the green beam will start. Exposure to the ultraviolet light source hardens the fluorescent material. The unexposed material remains soluble and is washed away with deionized water. This leaves us with a regular pattern of about 650 stripes of fluorescent material for green. 2 more suspensions are applied in turn. For each exposure, the light source is accurately located in the position of the appropriate gun. After the application of the fluorescent stripes, the screen is carefully checked. The ultraviolet light makes the stripes light up in their characteristic colors. But if we inspected it by daylight, it would only look like this. Each stripe is only 1/4 of a millimeter wide, and there are 2,000 of them. To improve the brilliance of our picture even more, we coat the fluorescent stripes with a thin layer of aluminium. A thin layer of varnish is first applied to the screen. Small coils of aluminium are placed under the glass, and the aluminium is vaporized in a vacuum to form a fine layer all over the screen. The aluminium layer is so thin that it is transparent to the electrons that will later pass through it. The shadow mask is finally attached to the glass screen. And a metal shield, which is needed to screen off the effects of the Earth's magnetic field, is fixed in position. Now, the completed front end of the picture tube is to be joined to the cone and neck assembly. The cone, to which we have already applied the glass bonding paste, is mated with the screen assembly very accurately. And they commence their journey through an oven 40 meters long. The glass bonding paste melts, and the glass of the cone and the screen fuse together to make a strong, vacuum-tight seal. The varnish we applied for aluminizing is also vaporized, and our picture tube is now ready for the electron gun assembly. The electron gun assembly is inserted into the neck of the tube. And is carefully positioned before it is automatically sealed in. Evacuation of the picture tube takes about 2 hours. During this period, the tube is heated to over 300 degrees Celsius to release any occluded gases in the metal parts and enable us to obtain a long-lasting vacuum. Finally, the tube is sealed off at the pumping stem and the remainder of the stem is removed. The getter is fired. A connection is made to the heaters to precondition the cathodes, and the electrodes are sparked off by high tension. Every vital function of each picture tube is checked at this stage. The tube is inserted into the test bay and is first demagnetized. Then a check is made of its electrical and geometrical properties, like cathode emission, insulation to high tension, beam landing and convergence. The basic principles for the self-convergence of 3 electron beams were patented by our company in 1954. But it has taken many years of pioneering technology to make massive quantity production possible of the most successful range of color picture tubes in Europe today. Every part of the final picture tube is now just as we intended, with the protection of soft flash and the high brightness we call high bri. A band of glass cloth soaked with resin is wrapped around the edge of the picture tube, and a heated metal rim band is shrunk on. As well as reinforcing the tube, it gives us a means of securing it to the inside of the TV cabinet. Finally, we spray the tube with a conductive coating on the outside to electrically balance the coating on the inside. This is the final examination. Our color picture tube has passed all its tests, and off it goes on the conveyor belt to the packing department. Where it is carefully packed into cartons to protect it against shock and damage during transit to any part of the world. In practice, what we have seen here in so little time takes 24 hours. 24 hours of applied technology, precision and automation, of inspection and checking at every stage of production, by impartial measuring instruments, by watchful, critical eyes, backed by continuous research and enormous financial resources, our color picture tubes will maintain their leading position among the most successful in the world today. And when tomorrow people meet again, even at an unusual hour, to share with others events like these, we know that television has caught their attention once more, thanks to the color picture tube. Television, the most rapid, the most vivid means of communication of our time, has captured the reality of the moment naturally, in color.